is approximation method. So so far we've been talking about Schrodinger equations in general, and so far you've only solved, you've only seen how to solve one Schrodinger equation. We did in detail the problem of the finite square well, and you guys all know how to solve the infinite square well. And how many others are solvable? There are about 6. Okay. So, and they're only 1D pretty much. They can all be reduced to 1D by separation there. There are about 6 of them. So, and the analytical methods, they're nice to learn. They're smart, but they're not very useful. Okay. So, approximation method is an extremely important part, especially in quantum mechanics. Okay. So, let's consider this this Schrodinger equation problem for an eigenstate. So we call this an eigenvalue problem. Right. So the eigenvalue problem, and the first step to start with a quantum mechanical picture, if you have the Hamiltonian given, then you just try to find its eigenfunctions, right? Because once you find the eigenfunctions, everything, time dependence can be solved by expanding onto these eigenfunctions. Right? So now, how do you solve this in general? Okay. Now we can use a trick called inserting the identity operator. I can choose some complete set of bases in the Hilbert space and work with them. Let's say that they are renewable. Okay. Then this complete set of bases, I can construct the identity operator from this basis. So why? I want to take a minute to make sure everybody understands. So why is the identity operator written this way? Is there another problem? Yes, but that's say one term is another term. What is so special about algebra? I want you to use direct notation to think about it. If I was acting on some state, it would be just, the first step is to project this onto that state, right? And then this gives you a number, let's call this f of n, right? And then the second step is to span this function, okay, onto this basis. So nothing has changed. So when you insert the identity operator, all you are doing is doing an expansion, right? Okay. And insertion of the identity operator is an extremely powerful method, and you will use that more and more in quantum mechanics. So you need Taylor series, and you need to know how to do this. That can take you pretty far. Okay. So let's go ahead and insert the identity operator. And as we define here, let's call this f of n. So we get that we can factor the eigenvalue E out. How do we make sense of this? Well, we can turn this into a component equation by saying.
So E is a function of n, isn't it, when you do it that way?
It's En.
Why is that?
Is your E an eigenvalue?
Yeah, E is an eigenvalue for phi, not for En, not for n. And I'm
E
just
is
saying.
a number.
Yeah, so the phi is an eigenvalue of the Hamiltonian, okay? But I'm expressing this on some complete basis in that Hilbert space. That basis doesn't have to be the eigenvalue of the Hamiltonian. Okay, doesn't have to be the eigenvectors of the Hamiltonian. All right. Otherwise, that expansion will be quite useless. If we already know this basis, why am I solving this problem? Okay. So to make sense of this, we can turn this into a component equation, and this you will do again and again. So the technique is to because this complete orthonormal bases are orthonormal, right? So if I test this equation with one of the bases, okay. I do this operate. I multiply by this bra from the left side. Okay. So that will give you and because of orthonormality, what is it? This is just the Kronecker delta function, right? All right. So now we can remove the sum by this Kronecker delta function on this side. Okay, so we get that. And let me introduce a new notation. We're going to see this is like the matrix element of this Hamiltonian operator when it's expressed on this basis. Right? So this is just HMN, okay. So why do I say this would be a component equation? If you now think about the Hamiltonian as a square matrix, okay, a summation over the HMN multiplied by this is like I'm going to multiply a square matrix by a row vector, right? Yeah, and then I'm basically computing for each n. Right? I'm computing a whole row, so it looks like this. Okay, so the m's row, okay, and then you go across because you sum over n, and this. What does this give you? This gives you one new element in the function, in the operator. It gives you the nth element here in your new and we're saying that after you do this multiplication, the vector doesn't change because this produces another element of the vector. This is the meaning of an eigenvector. Right? So this is why we say it's a component equation. So if I did this for every component, okay, meaning if I start with this side example. If I did this for every component, right, I would basically recover the full matrix equation. And that would be the matrix eigenvalue problem. Let's use double bar to denote matrix and then a single one to, now this is the vector now, this is not the expectation value. Okay, so this is more if you're familiar with this is just matrix equation. Right. So when we say the Schrodinger equation, which is a differential equation, is analogous to a matrix equation. Okay, it really is. And this is why. Now, if we knew this matrix, the next thing to do is what? Invert this matrix equation. Yeah, but you see that knowing this matrix amounts to computing these matrix elements on the spaces that we have chosen. Okay. But if I have an infinite basis, that matrix equation would not be solvable. It would just be as useless as hopeless as the original differential equation. So what do? In this sense, we must use a subspace. We must truncate this summation, saying that maybe for what we care about, only certain energy values, maybe only certain blocks of this are important. So I'll just do everything in that block. Okay. So this is the subspace projection. Okay. So to think about this, you can say you can think about the easiest case of this. So in 3D Cartesian coordinates, okay, x, y, z, right? Now, a complete basis in this vector space is what? any three mutually orthogonal vectors, unit vector either. So I can say that if I start from some point, and this point doesn't matter, it's just where I choose the origin. If I construct any three mutually orthonormal vectors, that forms the basis in the three-dimensional vector space. So now, if I have some plane, and all I care about is what's happening on this plane, or all I care about is what's happening. Most of the things that's interesting is happening close to this plane. What can I do? Well, what's a smart choice of the coordinate? It would be to take the normal of the coordinate and then use the two arbitrary vectors on the that spans the plane. So the plane is a subspace of the three-dimensional space. Right? And when most of the problem is happening in this subspace, we typically choose our coordinate system so as to just span this subspace. And whatever is coming out of the plane doesn't if it's not important, we just neglect it. So this is a picture of the subspace projection. Tells us how to choose this. And we still have some freedom to choose this basis function, because the whole plane has an infinite number of basis functions. But now if my problem has some special axis, then that fixes it once again. So then you can choose a basis that way. And this is what you do in quantum mechanics too. You analyze a problem, think about whether it has some special, whether a certain direction or a certain set of functions is important. Then you just use that basis, and you forget about the higher order basis. Okay. So this is the subspace projection method. Now there's a more flexible way to do this, and since we're using computers, modern computers can solve not just eigenvalue problems, but more general eigenvalue problems. So if we started from here, okay, and we do not resort to the method of reverting the identity operator, what we can do is just expand this onto some basis. And that basis doesn't necessarily have to be orthogonal. Okay? You do that at the expense of solving a different eigenvalue problem. So if I started here, before I move on, are there any questions of this subspace projection so far? No. Okay. You'll get a glimpse of actually using this when we later study the type binding model. Okay. Because in that type binding model, we're just saying that is a very intuitive subspace projection because we're just projecting onto the eigenstate of x. So we neglect the value of the wave function out there. Say I have some common well. You did this in the homework, right? I have some common well. Okay. Ground state looks like this. Okay. So now I can say that if the well barrier is high enough, ground state is going to decay away quite rapidly. Right? So most of the features of the wave function is going to be encoded over here. I can just forget about things over here. So when I'm doing this, essentially I'm saying that, well, if I'm taking the entire real line, then the eigenfunctions for the x operator is x minus delta x prime. And x prime will vary across the whole real line, so I have an infinite number of eigenfunctions. But since these things, they die out, I might not care about things beyond a and minus a. Right? So sometimes, a lot of times, people approximate this with an infinite square well. In that case, you are essentially doing subspace projection. And the subspace you're using is actually the eigenstates of x. Okay? And then later in the type binding model, you did something similar in the homework too. Okay. So when you think the homework is a bit difficult or whatever, okay, they have a purpose. Okay. Right. So when I'm doing this, what we're going to do is say, there are two wave functions here. I'm going to say that, well, because of this barrier, this wave function doesn't really know the existence of this thing over here. This wave function doesn't really know the existence of this thing over here. Okay. And then we're going to start with it. So really, this is an example of subspace projection method where you neglect some eigenfunctions of the X spaces. Okay. So any questions? No? All right. So let's move on to. So we can use a more flexible basis. It doesn't really matter that it's orthonormal. Okay. So let's imagine expanding phi onto some finite basis. I mean, since that f limit is already used, let me use it. Okay. Okay. And now this finite basis doesn't have to be orthonormal. Okay. So they don't really form the identity operator. You can't really use that. But you want to choose this finite basis because it's convenient. Okay. Because it represents the wave function well. For instance, if I did everything in the x-axis. So, well, let me see if you guys understand the direct notation right now. How do I turn this into a wave function on the x, represented on the x-axis? Yeah, you multiply by the bra of x. Right, you project this onto the x-axis. So now this turns into the wave function. Right. Over here, this turns into these eigenfunctions, right? And how do you compute an? An is equal to what? Phi and phi. Okay. How do you turn this into x representation? You insert the identity operator. An is equal to integral over x, phi and x, phi. Okay. And then this goes into, because this is in reverse order again. Alright, so then you integrate to get this. So you must be able to do this in your head to be familiar with direct notation. Okay, so now if we're thinking about projecting this onto the x-axis, then maybe my wave function has some form. Maybe it looks like, for a section it looks like this. Okay. Then a convenient basis I can use are, you can certainly use squares. Okay. Things like that. Okay. These would be orthogonal, but they will not be normalized. Okay. And another thing you can use, and something that's typically used, because if you're doing squares, then you need a lot of basis functions if you want to be precise. Okay. Things you can do is you can use triangles. And I'm not really going to be quantitative here, so maybe these two triangles add up to here, maybe here. So you approximate this function piecewise. Right. Now you see, take any of these two triangular functions. Are they orthogonal? No, right? They have overlap over here, so they must not be orthogonal. But that's okay. So now I go ahead and do this expansion on both sides. Okay. Let me use one. So that would be now if I tested this with the m's with the m's basis function, I would get Now, because the because the bases I have chosen do not have orthogonality, this is not going to turn into the delta function, but the quadratic delta. So this is in general some value that's indexed by m and n. Right. This just gives the overlap of each of the basis function. Over here, this is again just a Hamiltonian Hamiltonian matrix represented on this basis I have chosen. But you can still say this is HMN, right? So this, I can still turn this into a component equation. But the difference is now I have also a matrix on this side. Okay? So this is like, I'm saying, this row dot this column vector is equal to E times the same row of some other vector possible with this column vector. This would be this. This is called the generalized eigenvalue, and it looks like this. And let's say that this matrix is called the B matrix, and let's use the capitalized. Alright, but for the computer, okay, the computer can solve this. And if you chose your basis function well, maybe this n can be a small number, and you can accelerate solving pretty quick if you don't care about some details. Alright. Now, so these things are actually really useful, but we can't really teach too much about them in the course because you can't do them on paper. The easy thing would be to do the two-level system, which we will study later. And the two-level system is actually just doing this. When you have only two bases, it's very easy. You can maybe do it on paper, but in general, you should do it on the computer. All right. So this is one way to solve the eigenfunction using the computer algorithms. Now there are also things that you can do on paper, and we're going to teach those things in class. And these are not just mathematical methods. The results you get by doing perturbation theory have a lot of physical meaning. Okay, so now we're going to start talking about perturbation theory. And are there any questions on this? This is just linear algebra, so it's not really difficult. This is probably the most important topic that we have talked about so far. So first we're going to start with time-independent perturbation theory, and I've written it so that it's a non-degenerate case. Okay, the degenerate case we'll treat later, and we're also going to learn time-dependent perturbation theory later. Okay, so the time-independent perturbation theory, we're still concerned about solving this, in general, this equation. Okay. But now there's something special. Okay. Let's say we can decompose this Hamiltonian into two parts. We can decompose this into some Hamiltonian plus a small value, a perturbing Hamiltonian. Okay. Now the good thing about this is now we know we have a complete basis available for the unperturbed Hamiltonian. Maybe this is an exactly solvable problem. Okay, like maybe this is the unperturbed Hamiltonian is the infinite square well. Okay, so we know complete basis would be the sinusoids, right? So this perturbing Hamiltonian might be, okay, maybe I have a slanted well, slightly. You did this in the homework, right, before a finite well. But of course, you know, as we said before, we're using the subspace projection method of thinking. A finite well, okay, can be approximated as an infinite well for low-lying states, right? Because the wave function dies out quite rapidly. There's not really difference. Okay. So this method, if I'm talking about low-lying states, you know, I can use this H naught. I can use it to be the eigenfunctions of a infinite square well and actually solve or approximate a finite square well problem. It's still okay. And that is a combination of perturbation theory and the subspace method projection method mode of thinking. Okay. Another example is later, or maybe we're going to, so you know, the hydrogen atom, okay, the atom, a Coulomb potential atom, is actually exactly solvable. And when you solve that, and you consider an atom placed inside an electric field, and you're thinking about, well, what's the likelihood of the atom emitting a photon or absorbing a photon, etc. Then you will need to use perturbation theory again, because you have available a complete set of bases of the Coulomb potential problem, okay? And you just add perturbation to that. Okay? So these are just examples. But in general, okay, to treat this problem, we're going to do Taylor series expansion again. Okay? Sort of like Taylor series expansion, but we're going to insert a tunable parameter called gamma. Okay. And we're going to attach this to the perturbing potential. And this gives us the ability to dial the strength of the perturbation. Right? At 0, you expect that all the eigenfunctions should be the original unperturbed eigenfunction which you solve for. And then when gamma goes to 1, the perturbation is full strength. That's what you get. Right? So this, by doing this, really it allows us to, because we're doing approximation, right? By inserting this factor, it allows us to keep some terms and discard some terms, depending on, have a control of the accuracy. Okay. So this is the problem we're going to solve. And now, how many unknowns are there in this equation? This is an arbitrary parameter you're going to use. This is given, this is given. We're solving for phi and E together. So there's two sets of unknowns. And we are going to expand both unknowns in terms of this parameter. Okay. I'm going to say that E has a power series expansion. So first order is going to be independent of the dial over here. And then there is a linear order term, quadratic term. Okay. And then the same thing for the wave function. Okay. Now let's use a different notation for the wave function expression. Okay. So the 0th order. First order, second order. And you rarely go above second order in perturbation theory. So this is, it's actually, even though this method is simple, the algebra is quite complicated. Okay, so what would be the phi 0? Okay. It would just be an eigenfunction of the of H naught, right? So an unperturbed Hamiltonian. Because if I were now to set the dial to 0, right? If I set the dial to 0, you get that the eigenfunction must be an original eigenfunction. So now let's go ahead and write this equation out. what we're going to do now is, since we have this dial, right, and let's match terms and powers of gamma, because now both sides are series expansions, right? If I have two series expansions, right, alpha 0 plus alpha 1 gamma plus alpha 2 gamma squared, etc. Then I have beta 0 plus okay, and I said they're equal. How do they, and they're equal for an arbitrary gamma. What does that mean? They're equal term by term. Okay. So, and is everybody okay with this? Do you all know how to prove this? Okay, so it's very simple. Okay. Since this is arbitrary, we can set it to 0. If I set it to 0, this is proves that the zeroth order term are the same, right? Now I treat this as a variable, right? It's arbitrary, so I can treat it as a variable. I take that derivative, right? First order term vanishes. Okay. If two things are equal here, the derivative must also be equal, right? And then I bring this first order term down to the zeroth order term, and then I set that to 0 again. They're equal. Right? So the power series expansion work. So now let's write down the zeroth order terms. Okay, so the zeroth order terms, well, on the left hand side we have this and this, nothing else. So the zeroth order term is actually just the eigenvalue problem of the omnitreptine component. Over here you have E naught dependent, nothing else. Right, that's the zeroth order term. And we have stressed this many times. So then let's write down the second, the first order term. And the first order term is this multiplying with this. Okay. So let me label them here. You're going to get this term. Okay. And then you're going to get this multiplying this. That's it for the left hand side. Okay. So on this side, okay, first order, you're going to get this and this, okay, and then this term and this term, and nothing else is first order. Okay, so let's go ahead and write. Okay, so now, how many unknowns are here? This is given. Okay. This is given. This is given. These two, the phi 1 and the E1, are what we were looking for. Okay, so let's rearrange this problem. So let's put all the known quantities on one side. Is that true? Yeah. That's what we're doing. Well, yeah. Oh, sorry. All the known quantities on one side. So this is completely known, right? What else is completely known? Nothing else. Yeah. So phi 1 and phi 1, let's combine the first order correction in the wave function. Okay. So that would be h naught minus phi 1 is equal to, put this over here, d1 So why haven't we arranged it this way? Actually, these two are not very different. Right? They're not very different in the sense that if I now test this equation with the eigenfunction, phi 0. If I test this equation with phi 0. Phi 0 and phi 0, this is a number, gives you minus phi of right? Okay. Now if I, oh sorry, okay. Now if I think about this as an operator operating on a graph from the left, then this goes over here, and you see this gives you the eigenvalue, which is just D0. And so this side is 0. On this side we have right. So we get that for the energy, so first order approximation. The correction in the energy is just the excitation value of the perturbation taken with respect to the arbitrary wave function. Okay. And this equation, okay, you should just memorize this. It's used everywhere. Okay. So now that we know what E1 is, okay, we can go ahead and plug E1 into this equation, right, and solve for phi 1. But to do that, let's expand phi 1 onto a set of onto the eigen